Everyone. Welcome back to another lesson in MCV4U. Today we'll be looking at the applications of the dot and cross product. So if we look at work, again, work is a scalar quantity that is measured by joules. So it's again, a scalar quantity measured in joules, defined by the product of the distance an object has been displaced and the component of the force in the direction of the displacement. In other words, when a force is acting on an object so that that object is moved from one point to another, we say that the force has done work. And recall the formula: force is equal to mass times acceleration. And work is work done by a force is defined as the dot product. So work is equal to the force times the displacement. Again, here we see that the force is in newtons, the displacement is in meters, and the work is in joules. So again, here we see that this is the dot product of the two forces. It does not symbolize scalar multiplication, but it's the dot product between the two forces. And here, so this is scalar multiplication, and we see here that work is equal to the magnitude of the force times the magnitude of the displacement cos theta, where theta is the angle between the displacement and the force. So here, if we look at a couple of examples, again, it says a sled is pulled with a force of 25 newtons by a rope at 32 degrees to the horizontal. If the sled moves 1.8 meters horizontally, find the amount of work done. Here, if we draw a diagram, we see here again the sled is pulled with a force of 25 newtons. Again, by a rope 32 degrees to the horizontal. And if the sled moves 1.8 meters horizontally. So here, to calculate for work, we have dot product of force and the displacement. So here, that's also equal to, again, the magnitude of the force times the magnitude of the displacement cos theta. And so here, work is equal to 25 times 1.8 times cos 32 degrees. So here we see that the work is equal to 38.2. And again, work is in joules. Example number 2 says a force 15 newtons along the vector v is equal to -2, 4, and 6 moves a particle from A, 6, 1, 4 to B, -2, -3, and 7. Find the work done if the distances are in meters. So here we see that we have A, which is at 6, 1, and 4, and it goes to B, which is at -2, -3, and 7. We see that the vector is -2, 4, and 6. And here we can see that this would be 90 degrees. And again, if it has a force of 15 newtons. This is 15 newtons, and the vector here is equal to -2, 4, and 6. So here, again, in order to find the work, we need to find angle theta. Okay, so first thing here we'll do is we'll find the magnitude of this vector here. So here, when we find here, if we look at the magnitude of our vector, it's going to be x squared plus the y squared plus the z squared. So that's going to be 4 plus 16 plus 36. And that's going to be equal to square root 56. And here we see that our force, again, of 15 newtons and is a scalar multiple of the vector. And so here we see that magnitude of our force is equal to k times the magnitude of vector here, vector v. And so here that we know that 15 is equal to k times square root 56. And so 15 over square root 56 will be equal to k. And here we know that vector AB so here we see that vector AB will be equal, so here B minus A, so here -2 minus 6 will be -8, -3 minus 1 will be -4, and 7 minus 4 will be 3. Here, therefore, we see that our force will be equal to 15 over square root 56 times -2, 4, and 6, which is our vector here. So here we can calculate that work is equal to our force times vector AB. Okay, so here we have 15 over square root 56 and we have -8, -8 times -2 plus -4 times 4 plus 3 times 6. Here we get an answer of 15 over 2 square root 14 times 18. Or we can simplify that. Cancel out the 18 and 2. And or we can just write it as 135 over square root 14 joules. Okay, so the next thing we'll look at is, again, here, if we look at the magnitude of the cross product. So, again, the magnitude of vector A times vector B is equal to the magnitude of A times the magnitude of B sine theta. So here, if we look at the area of parallelograms and triangles, we know that, again, area is equal to base times height, which is equal to the magnitude of B times H, which is equal to the magnitude of B times the magnitude of A sine theta, so that's equal, which is also equal to the magnitude of A times the magnitude of B sine theta, and which is equal to, again, the magnitude of A times B. So here it says to determine the area of the parallelogram created by the vectors U, and created by vectors U, 1, 2, 3, and vector V, which is equal to -3, 1, and 2. So here, if we look at the cross product vector U and vector V, that will give us the area. So here, if we write our first line, again, it'd be 1 and -3, 2 and 1, 3 and -2. And then here, again, we will rewrite, we'll get rid of this first one here, but we'll rewrite it. So we'll rewrite it as 1 and -3, and we'll rewrite as well 2 and 1. So here we will then apply the cross product. Here we'll have -4 minus 3, which is equal to -7. We'll have -9 plus 2, which is equal to -7, and 1 plus 6, which is equal to 7. And so here we see that the cross product of U and V is equal to -7, -7, and 7. So here we will find the magnitude of the cross product between U and V, which is equal to square root 49 plus 49 plus 49. So that's equal to 7 square root 3 units squared. So here we see that, therefore, the area, when we calculate it, is 7 square root 3 units squared. And then here, example 4, it says find the area of the triangle PQ and R with the vertices 3, -1, and 4, Q, which is 7, 2, and -2, and R is 6, 3, and -4. So here, if we draw our diagram, we have, here we have P, Q, and R. And here we're given the formula. So again, the area of the triangle is equal to the area of the parallelogram divided by 2. And so first we'll do a couple of things. We'll let C vector PR is equal to B, and we'll let vector PQ equal A. So here, therefore, we see that the area of the triangle PQR is equal to, again, the cross product of A times B divided by 2. So see here, we see that vector PQ is equal. So if we're given our values again from P to Q, so here we have 7 minus 3, which is 4. We have 2 minus minus 1, which is 3. And we have negative 2 minus 4, which is negative 6. So that's for vector PQ. Vector PR will be equal to 6 minus 3, which is 3. 3 minus minus 1, which is 4. And negative 4 minus 4, which is negative 8. So here, if we're looking at the cross product of A and B, and we'll write our first line, 4 and 3, and 3 and 4, negative 6 and negative 8. And then we'll rewrite the first two lines as well. Take out the first line, so here we have 4 and 3, and 3 and 4. And we'll apply the cross product here. So here we'll get negative 24 plus 24 is equal to 0. We get negative 18 plus 32 is equal to 14. And we'll get 16 minus 9, which is equal to 7. So here we see that the cross product of vector A and vector B, which is vector PQ and vector PR, is equal to 0, 14, and 7. So here we can find our magnitude of the cross product of vector A and B, which is equal to, again, x squared plus y squared plus z squared. Here, x squared is 0. Yeah, y squared, which is 14 squared, which is 196, and 7 squared, which is 49. So that's equal to square root 245. So the area, again, of square root, sorry, the area of the triangle of PQR is equal to the square root of 245 divided by 2, which can simplify to 7 square root 5 over 2 units squared. So here, therefore, the area of triangle PQR is 7 square root 5 over 2 units.